recording. So, okay, hopefully you can all see my screen, everything's good. And all right, so we're finally going to start doing physics right now. The thing that I talked about day one was this class is all about motion. So starting with Newton observing an apple falling and trying to find a way to describe that motion mathematically, and then make predictions about what would happen if, say, he had a rock and an apple, how fast each one would fall from different heights. He came up with his laws of motion. It's something I asked you about in the quiz last week, just to see if you knew them. There are 3 of them. We're only going to talk about the second one today. Next week, we'll talk about all 3 of them and how they all relate to each other. But the second law, and this is super important, this is one of the most important slides to think about for a long time. So Newton's second law states that force is equal to mass times acceleration. And what that equation means is a lot crazier than you might have ever thought. We kind of accept it as F equals ma, plug in 2 for F and 3 for M and you get A. But there's a lot more going on here, and you have to go back to being Newton for a second. Imagine you were Isaac Newton and you're trying to figure out how to describe how something falls towards the earth, right? He had to come up with definitions for force and mass and acceleration. And you might think you know what those words mean, but I don't know why my dog is now pacing. But I want you to take a second to think about what those words actually mean and if you can define them. Now, a force is something that moves an object, right? That's probably the simplest way to describe it. Whenever something causes the motion of an object to change, we say it applied a force. And that's kind of circular reasoning with this definition. If we're trying to define F equals ma, to say, well, force is mass times acceleration, but anything that causes the motion of an object to change, and by motion we mean specific things, which we'll talk about in a minute, is a force. So what do we mean its motion changes? And I'm going to jump down to acceleration here. When we describe how an object, hang on, do not bark. You can go outside and do good, but don't bark. So when we talk about an object moving, you're all familiar with speed, how fast you move. If you run across your room, you can say you ran at 8 miles an hour or something. You drive your car goes 60 miles per hour on the freeway. You know what speed is. Speed is velocity in a way. We'll talk about that. But speed is how your position changes. That's why it's miles per hour. It's the distance you go over time. So in a certain time interval. Acceleration is how your velocity or speed changes with time. And it's far harder to envision than you probably think. For the most part, you can envision a car starting from rest and speeding up until it reaches some speed. So like doing a burnout. But how that car's speed changes is not quite as obvious as you might think. But a force causes an acceleration, which means it causes the motion or the velocity of an object to change. However, if the object has mass, how does that affect a force? More importantly, how does it affect acceleration? And so we come to the question of what is mass? So acceleration is change of speed or velocity, whichever word you want to use right now, will be more correct in a minute, with time. And what is mass here? Well, we know that mass is like how much stuff something has, but there's a better definition of it. And that definition of mass comes straight from this. If I divide through by m on both sides, I get that the acceleration is the force divided by mass. The more massive, well, let me apply a 20 Newton force. The more massive an object is, the smaller acceleration it gets. So if you push on the ground with a 20 Newton force, the Earth's mass is so huge that you can't accelerate. However, if your mass is very small, like say 1 microgram with a 20 Newton force, it's going to accelerate really, really fast. So one way to think about mass is it's how an object resists motion changes, okay? Due to force. And that's all we need. A force is something that changes an object's velocity and acceleration. And mass is how well that object resists its motion changing. And acceleration, just the change of velocity with time. That's what we're going to go over in 1 dimension today. We're going to do a little bit of 2 dimension, but it all starts there. That description allows us to understand how cells get moved around in a blood cell. It allows us to see how an object gets bent, how a baseball gets hit, how we walk, all of these things. There's more to it, which is why there's 2 other laws that Newton gave. But for the most part, what he did, and the genius of Newton, was that he defined a force, a mass, and an acceleration to understand motion, instead of just saying, hey, that thing went that way. Okay, so we're going to go through, and I'm going to go grab my dogs really fast, and then we'll go through this. Come on. Up. Come on. I'm sorry, I will never understand. They will be totally happy and content until I come down here to start a meeting, and then they all want something. So, okay, so to understand acceleration and velocity, speed, we need to start with displacement, the simplest thing. An object moves from point A to point B, right? So when it does, we can put this on an XY grid if we want. We could say A is at the origin and B is at 10, whatever units we happen to be in. But whenever we do, go play. Whenever we do a delta, and this is really important, delta anything, it's always final minus initial, okay? So here, if we're going from A to B, our delta X is B minus A, final minus initial. Where B is 10 in whatever units we want, and A is 0, this would be 10 minus 0, or 10. Let's say it's in meters. Go play, get. No, go. All right, so that's displacement. I think you all understand displacement. The only thing to remember is that that delta, that change of X, is always final minus initial. Don't confuse that, and it's super easy to do. Now, we have something called average velocity and average acceleration. This is usually what people mean when they say speed. Physicists hate the word speed. Wiley Plus loves the word speed. Speed is the magnitude of B. It has no direction. So if you say you drove to school at 60 miles an hour today, you're talking about your speed. You're not saying you went east or north or came from, northeast. You're just telling us a magnitude. The reason why physicists don't use that is it doesn't tell us anything. It's not a vector, it's a scalar. And it's completely useless for describing motion other than in the most general terms. These two things are vectors, okay? And remember me saying that I'm gonna leave this stuff off. In general, I am. We understand that this is a vector, that it has a direction. The direction in one-dimensional motion will be in the x-hat direction, right? So this is still in the x-hat direction. A lot of times I'm just going to leave it off and assume that you understand that it is a vector. Second thing is this is an average value. So the average value just means take the change of x over the change of time. Okay, so if I go from 0 to 100 meters in 20 seconds, then T1 is 0, T2 is 20 seconds, X2 and X1 are 100 meters and 0. And this would be 100 minus 0 over 20 minus 0 meters per second. 100 divided by 20 is 5. And so my average velocity during the first 20 seconds of my motion is 5 meters per second. That might not be my speed at any time. My velocity could have changed. This is an average value, which means after 20 seconds, I was 100 meters away from where I started, and therefore my average velocity had to be 5 meters per second. We don't use average velocity because of that. We're going to talk in a second about instantaneous, which is what we use and which is why you need calculus for the class. But average is somewhat useful sometimes. It's important to know what you mean, and we will go through that with some graphs in a minute. But average acceleration is the same thing. But now let's say V2 is 5 meters per second, but let's say we started at rest. So rest means that your velocity is 0. And remember, again, these are in the x-hat if you want them to be. It's assumed that you know that. And then our time will still be our 20 seconds, and our time 1 will be 0 seconds. We almost always assume our initial time is 0 because that's when we started measuring. A lot of times we'll assume that our x1 is also 0, unless for some reason we need it. So here, what we get is that our average full acceleration is 5 minus 0, v2 minus v1 over t2 minus t1, or 1/4 a meter per second squared, because this is meters per second and this is seconds. Okay. Velocity and acceleration are very different quantities. The acceleration, if we started from rest and reached 5 meters per second in 20 seconds, we have to, for the average acceleration, divide our velocity, 5 meters per second, by the time. So how long did it take us to accelerate to get there? Okay. Again, we could have accelerated in the first second from 0 to 5 meters per second, and then just stayed constant, and that ended up being our average. You'll see that both of these average values really are unhelpful, except in certain cases. But they're in the book. You should know how to calculate an average value, I'm assuming. Hang on, there's a quiz or a chat message. You should be able to do it in the quiz, Fernaz.
In the quiz section, if I wrote down, but I wrote down on the paper and I scan it and I want to send it, but there is no assignment there.
Right. You can actually insert it as a quiz answer.
How? I don't know how.
Okay. So
Sorry.
I go to my quiz. Let me share my screen. Sorry, I don't know why this is.
For example, in the assignment for lab, there was assignment that we could
Yes,
scan it.
I know. Let me show you. There is not that. What you can do is in the actual quiz itself, you can go into your answers, and right here where you would answer, there's an insert. When you click on that, you can insert and upload an image. Are you able to do that, Farnaz?
I should try. I'm not sure if I can do it with my phone.
You should be able to do it. Let me know if you can't.
Okay.
Um,
Cannot you open the assignment like the lab? Then I can scan and do it.
yeah, I know.
It's so easier.
You should be able to really, like Hamad said, it's really easy to just insert it right there.
Okay, I will try. Thank you.
Yeah. Yes, Sammy.
You can take a picture, or you can take a picture and upload it as a picture, or you can save your file as a document, Word document or PDF, and then upload it. It's very easy. I tried it. It works.
I'll try it. Thank you.
Thank you, Hamad. So Shota wanted to know, and I will go back to share screen. I want to share my PowerPoint. And I would really prefer, if you guys have questions, just say them. Yeah, you have to show your work normally for a quiz. On this first quiz, no. If you don't show work, it's okay. And in general, if you get the question mostly right, you'll get full credit. It's only worth 3 points. So the difference between 2 and 3 is basically not answering questions or getting stuff very wrong. So Shota asked, what conceptually is a unit squared here? So I really think I can answer this best when we talk about instantaneous acceleration and velocity, Shota. So I will come back to your question and you'll see it. But basically the short answer is velocity is position over time. It's the change of your position with time. So it's meters per second. And acceleration is velocity over time, which is meters per second. That's where a lot of people have a problem visualizing acceleration. You kind of know it. You put your foot down on the gas pedal of a car, the car accelerates. But it's really weird. It's kind of one of those things that intuitively you think you understand it, but you don't quite understand it. How your speed is changing is your acceleration. Put another way, when you slam on your brakes to stop your car, your velocity is quickly going from some value to 0. Your acceleration is how your velocity is changing, how fast your velocity is changing. And your acceleration is negative because your velocity's going from some initial value to some final value that's 0. So it's 0 minus initial. We'll see that. We'll do some examples. Hopefully it'll kind of make sense. Now, I know you all know how to do really easy derivatives. If we had a position function, and I'm going to do a really simple position function, where we have some x that depends on t is 4t, let's say, 4t squared. in the x hat direction. If we want to know at any time, let's say at a time 0, at a time 0.1 seconds, at a time 3 seconds, at a time 1,000 seconds, right? In order to find the instantaneous, the velocity at that instant, we have to take the derivative. The derivative is how a function changes with time, the derivative with respect to t. The derivative with respect to any variable is how the function changes with respect to that variable instantaneously. So you can talk about like a graph that is x versus t, and we will. The slope of this graph is the derivative, the slope at every point, but we can see that that slope is changing at every point, right? So here it's positive, probably, I don't know, 1. Here it might be like positive 0.8. Here it's 0 because it's flat. Here it's whatever. The slope is the derivative of x versus t, which means it is the velocity, or at least the instantaneous velocity. Again, remember that this is a vector. So if we take the derivative of this, we get 8t in the x hat. But that's not the instantaneous velocity. That's the function of the velocity. In order to get it, we have to specify t. So at t is equal to 0, v of 0, this is how we write it. This is t is equal to whatever our value is. This is 8 times 0, or 0. V of 0.1 is 8 times 0.1, 0.8. And these are meters per second. On and on. 1,000 is 8,000. I chose a really simple function, right? But it could be a very complex function. You could have something really awful that was something like ln of t plus 8e to the 47t or something crazy for your function. The first derivative gives you the velocity. It's a little more complicated than that, but essentially the first derivative gives you the velocity of your particle. If x of t is the function that describes that particle's displacement. So what have we learned so far? What we learned so far is we have displacement, and displacement is a fancy way of saying the change of x or y or z or whatever your coordinates are. It's always 2 minus 1 or final minus initial. Velocity average is delta x over delta t. Yes, we'll get there, Lucas. So this is average v, which is x2 minus x1 over t2 minus t1. Now, you might have learned in math, the instant, that if you let x2 minus x1, the change go to 0 basically, in the limit, so v instant is delta x over delta t in the limit that delta t goes to 0, meaning as you scrunch everything down, that is another way of just saying the derivative. Okay, if you want to be mathematical about this, the instantaneous velocity is the average velocity for a very, very, very small interval, an infinitesimal interval. Okay. And then this same thing goes for the average acceleration. Accel average is the change of v over change of t, and the accel instant, which we haven't done yet, and we will, is dv dt. Okay.
Sir,
Yes.
I have a quick question on the instantaneous instantaneous velocity.
Yeah.
How do we get, like, on the final equation you wrote on that slide, was x of t equals ln of t plus 8 to 8e 4.7 t.
Mhm.
Where did the 4.7 come from?
I just made that all up. I'm just saying your position function could be something really gross. because I use this really simple function here, I just don't want you to think that it would always be something simple. It could be something disgusting.
Oh,
It's really hard to take a derivative of. Anyway, so ignore that. Just ignore that, Sam.
all right. Thank you.
I just wrote some garbage down. All right, so I grabbed these off the internet just to show you a few things, okay? So here's a graph that has position, x versus t. It has velocity in the second graph versus t, and it has acceleration versus t. I think they're supposed to be the same, but they're not, because this thing has some weird curves and stuff. And they don't actually quite work, but I'll show you that in a minute. So here, and these definitely are not the same graph. So the slope of an x versus t, we're just talking about this graph right here. The slope, as I said, is your velocity. So the slope here would be like -1. The slope here, v, is equal to dx dt, which is the slope is 0. Here, let's say it's 1, right? The slope of an x of t graph is the actual velocity at that moment, assuming a linear trend line. The reason why I say that is if we had some actual fit, it's a little bit different, but we'll get there when we get there. For now, just know that the slope of an x versus t graph is your velocity at that particular moment. Okay. Instantaneous acceleration is, as Lucas or Sammy or whoever it was said, it's the second derivative of the position, or it's the time derivative of the velocity, because it's d dt of x of t. So it's the time derivative of the time derivative. That's why we get the 1/2 squared. What this means is we had back here our function x of t was equal to 4t squared, taking the first derivative, which is the velocity. We just move that forward, we get 8t, and then taking the second derivative, which is the acceleration, we get t. I'm sorry, we get 8. Okay, and these were in the x hat, as we said, because they are actually velocity, or I mean, also, they are actually vectors. So what this means in this particular function is that the acceleration is constant. And that's something really big to understand here. If v is constant, all right, Fernaz, we'll figure it out together at some point, but you can email me, but I don't want everyone emailing me. Please try to insert it into your quiz if you can.
Okay, can I insert it in the lab after the lab assignment?
No,
Okay, well, email you.
I
Thank you.
don't want to do that. Just email it. Yeah, otherwise I have assignments for you all over the place that I have to figure out where they are. It's easier just to email me, but.
Okay, thank you. Thank you.
So if v were constant, so in our equation, if v of t were say 8 meters per second along the x direction, what is the derivative of this? So the acceleration is the derivative of v with respect to t, but it doesn't have a derivative. There's no t there. So I get 0. This is constant velocity. And that should make sense to you. Acceleration is how the velocity changes. If the velocity is constant, there is no acceleration. The velocity is not changing. That's actually the special case that led to Newton's first law that everyone knows. An object at rest stays at rest. An object in motion stays in motion unless acted upon by a force. So if the acceleration is 0, then the force is 0, right? And if the force is 0, the object's motion doesn't change. Its velocity doesn't change. So bear that in mind. It's one of the most important things that we have. you always have to know that if you're told the velocity is constant, there are no forces acting on the object, or all the forces are zero. That is one of the most important things to back up for a second. I think one of the hardest things about physics and doing physics problems is there things like this. You have to know that if it has constant velocity, all the forces add up to zero. That's just something you have to know, that you're not told that in the problem, right? If you're told, oh, a train's moving at, a constant velocity of 12 meters per second, and it's being pushed at this angle and pushed at this angle, well, if it's moving at constant velocity, all the forces are equal. We'll get to that next week when we do chapter 4, but it's important. Acceleration is the rate of change of the velocity. A constant velocity means a zero net force. And we'll talk about that. Yes.
Quick question. So in that equation, force equals mass times acceleration.
Mhm.
If you solve it for A, you have force over mass.
Yes.
So like if in that case acceleration equals 0, you would have 0 equals force over mass. But how can you have like mass equals 0?
That wouldn't be mass equals 0. That would be force equals 0.
Right, but force is in the denominator.
Nope.
I mean mass isn't. Oh,
Yeah.
okay.
Yeah, mass is always, so something that we're going to deal with all the way up until chapter 8, maybe 9. We're going to deal with something called the rocket equation, but
Mhm.
we're going to assume that mass is a constant value and that mass can't change. We're going to find out what to do when mass can, and you might ask, well, wait, how can mass change? Well, imagine you were running down a hill holding like some weight on your chest and you dropped one of them. So now all of a sudden your total mass changes.
Mhm.
It can change, but for the most part, it's not going to change in this class. So the thing I wanted to get across to you about mass is I don't want you thinking of it as stuff, as how much stuff something's made out of. I want you to think of it as its resistance to having its acceleration changed by a force. The heavier or bigger or more massive something is, the harder it is to change its velocity. Think about a train coming at you and you try to jump out on the tracks and stop it with your hands. That ain't happening, right? A fly, you can easily change it. So just think of it, I don't even know who that is, sorry. Just think of mass as the resistance to changing acceleration. Hopefully that makes sense. If it doesn't yet, it will eventually. So now we're going to look at the acceleration from a VT graph. So now we're looking at this green one. And again, the slope at any point. So here is 1, here it's say -1, and here it's -1 again. And at these points, it's actually undefined, even though it's 0, because it's instantaneously changing. Those of you who know math know that there's no point there, but we would assume that the acceleration is 0 at these inflection points. All I'm saying is that, again, the slope of a V versus T graph is the instantaneous acceleration. However, something kind of cool that you already know, I hope, is the acceleration is, the position, the total displacement, I got ahead of myself for a second. The total displacement is the area under the curve of the V versus T graph. How do you know that? Well, let's just treat d of t as if it were actually time. So we have meters per second here, and we have seconds here, and we get meters, right? And this is an area. If you had a box, you would have length times width would give you an area. So this is the area under the curve gives you x of t, right? So on a VT graph, the area under the curve is the integral, and that's equal to x. Now here we can see that we have 3 squares up and we're only going halfway. So this is 1.5. This is 1.5. This is -1.5. And this is 2 plus a half. So this is -2.5. Therefore, the area under this total curve, this is 3. This is 3, 4. So this whole area is -1. The area under the curve, I don't want to say that. Yeah, maybe. Let's not say that yet, Eric. But yeah, the area under the curve gives you the integral of VT. It's super helpful when you have a nice function, like we're going to see that the acceleration right here is nice because it squares, right? So if this is like 1, 2, 3, and these are 1, 2, 3, 4, you can go 1, 2 times 3. This area is 6. This area is 1. This area is 3, right? And you would have 6 minus 4, which is 2. Anyway, so the area of a under the curve is the integral, and that's kind of fun. One of the problems that I want you to again put yourself in Newton's shoes for a second. He realized that 2 masses had to attract. So the reason why an object fell towards the earth was the earth and the object were attracting each other. But Newton was awesome. It wasn't good enough to do the easy example. He would do every example. He would try to dig into everything and do it the hardest way possible. So he imagined that the earth was made up of a billion little pieces of mass, and every single one of them was attracting the object that fell. And he did the integrals, and he invented integral calculus to deal with large products and sums. And he developed integral calculus basically to solve the problem of an object falling out of your hand and hitting the earth. One of the cool things about integral calculus is the area under a curve of v versus t is the integral of v times dt. That's pretty cool, pretty awesome and useful, because, and I'm going to say this a bunch of times this semester, humanity is not the smartest creature in the world. Maybe we are, but we're still very limited. And any trick that we have that makes things easier for us to understand is really, really useful. One of the most useful tools you can have is that the area under a curve gives you the integral, because you may not be able to do the integral. You might not know the function. You might not be able to do the function. You guys have learned integrals, but you've learned simple ones. There are ugly integrals out there that are very hard, but you could graph it and have a program compute the area under the curve and get an answer. And that's crazy useful, because you don't have to solve the math that you can't solve any other way. Or maybe you don't know the solution and you want to check, you can verify the solution to this ugly equation with the area under the curve. It's really, really, really helpful. It's more of a mathematical digression. We'll never go area under the curve, but there's a section on it in the chapter. Okay, so as I said, the area under the curve of an AT graph is V, because this is meters per second squared times seconds in dt, and so we get meters per second, which is the velocity. All right, enough of that. The takeaways here, that when we have more than one direction, and this is why we care about vectors. This goes back to answering a question I brought up last lecture. Why do we care about vectors? Vectors can be broken into their components. So the velocity, the displacement, and the acceleration, we can break all of them up into X, Y, Z. We can talk about an acceleration in the Y, AY, and an acceleration in the X, and an acceleration in the Z, right? We can break a force, which is also a vector, into components. By breaking them up, we can solve them in one dimension, which is what we're going to do for the rest of this lecture. And then put them back together like any vector, right? So we can find how the velocity is changing due to a force, due to the acceleration from a force in the Y direction, and then put it all back together. We don't have to solve three-dimensional equations. We just have to solve one dimension. It's really nice, and we're going to do it in chapter 4 when we do projectile motion. But it makes everything easy. So now we're going to learn how to do velocity and acceleration in one direction and a bunch of problems to do with those. We can derive some equations. Now, I think I said the problem with physics is you can't memorize equations. You have to like know how to use them. These equations you can totally memorize. In fact, you're going to need to if you want to be fast at these types of problems that we're going to be doing soon. So there are what are called constant acceleration equations. When the acceleration is a constant, we're going to assume that therefore this is a constant. And we're going to do something that sometimes math people get mad at us for because we're physicists. We can take this and multiply both sides by dt. And so what we get is we get a dt is equal to dv, or better yet, dv is equal to a dt. And then we can integrate both sides of this one from v naught to v final. That little 0 just means the initial value, the final value, the initial value of time and the final value of time. I'm going to take the initial value of time to be 0, and I'm going to call v final just v. Okay, this is a constant term, and these are easy, right? So this is v final minus v initial is equal to a times t final minus t initial. But I said this is 0. So really what we get is we get that v final is v initial plus at. These are vectors, but this equation right here tells you the acceleration times time, and I really should leave it as a time interval, but you'll see that we almost always just write time as just a time. The final velocity is the acceleration times time plus whatever your initial velocity was. And we'll see that in a minute. So now that we have that, right? Well, what else can we get from this? If we call v naught plus at, and remember that this is a constant and this is a constant, we also have that v is equal to dx dt. So again, we can write dx is v dt, take the integral from x initial to x final, from t initial to t final. Again, t initial is 0. So what we get, and t final is just going to be t, we get x final minus x initial is, from 0 to t, v naught plus a t dt. This gets a t, this goes to t squared over 2. So we get x final minus x initial is v naught t plus a t squared over 2. This equation right here now gets added. So I'm going to write them right here. We got that v final was v initial plus at. We got that x final minus x initial was v initial t plus a t squared over 2. We can actually substitute in for v initial here and manipulate these in a little way. And I'll show you why we're going to do that in a minute. I urge you to do this for yourself at some point. And then there's one other one that we can get by just doing a bunch of algebra. And I'll talk about why we have these four. So we have these four. Your book also gives you one where there's like a negative B final. I guess. I don't ever use that one. I don't think that one's that useful. The reason why we're using these constant acceleration equations is, yeah, I will in 1 second, is that all forces, for the most part, 90% of the time, our forces are going to be constant in this class. And I'll show you what to do when it's not, but these equations are only for constant acceleration. So if I go back a slide, all I did on this slide was I used v is equal to dx dt, rearranged it, and I used this as my function for v, noting that v naught and a were constants. And I get this equation. One other thing I want to say, I wrote x here, but it could be x or y or z. When whatever these are, if these are x, then this is b initial in the x, b final in the x, a in the x. Okay. This is just the general version. Some of you may have learned the parabolic motion equations where you have negative g in here. And I have to break you guys of that habit. It's going to be one of the hardest things for some of you. We'll get there when we talk about free fall, but there's a negative sign and some of you have learned them and it's so hard to unlearn. If you don't have constant acceleration, you can do one of two things. You can get, as I said, x is the integral of v dt, v is the integral of a dt, b is dx dt, and a is dv dt, or the second. And these, again, could be x or y or z, whichever one you're in. So if we want vt here, we would take the derivative of this. 4 would come down, so 456 t to the third minus 6t. Taking this again, that'd be 150, 168 t squared minus 6. We could then ask, and remember, these are the instant. From t0 to t4, how far does it travel? Well, that's just plugging in 14 x final minus x initial to the fourth, but this is 0, so it's really, sorry, I'm being dumb. These are t's. T final minus t initial, but really you can get rid of that. So it's just 14t to the fourth minus 3t squared. Put in a 4 here. 4 times 4 is 16, times 4 is 64, times 4 is 256, times 14 is, so let me write it this way, 14, 4 to the fourth minus 3, 4 squared. So this would be 14 times 256 minus 3 times 16, 35, 36. Let's call it meters. What is a at t is equal to 0? What is b at t is equal to 4? If I plug in 0 for t, I get that a is 168, 0 squared minus 6, so I get minus 6. It's called x hat. And then v, when t is equal to 4, I would plug in 4 there. I'm sure you guys can do it. So if it's not constant acceleration, you actually need to go through and take the derivatives and maybe do the integrals. I'm not going to make you do that. We're going to assume constant acceleration, which means these equations apply.
So what is x? I'm kind of, I understand all the math you're doing, but
All I'm saying, Lucas, is we can go in any direction we want. So these equations, as long as the acceleration constant, and you'll see that when we do free fall in a few problems, these equations apply no matter what coordinate you're in.
Okay.
But a is a in the x direction, b naught in the x direction, b final in the x direction, if we're talking about x. If we're talking about y, it may be different. And we'll talk about that in a second. Okay, so just to use these constant ones, and I'll rewrite them right here. It would be very helpful for you to write these down somewhere and just keep them near you. And I'll explain, don't write them down right now. We'll write them in a minute because there's a better way to write them, or at least something important to write about them. And then, and keep in mind that these can be all derived from the first two. And the first two can be derived from the derivatives of the position and the velocity. Okay, so if a vehicle starts from rest and accelerates at 5 meters per second for 10 seconds, how far does it go? In these problems, what I recommend, and this is something that some of you is going to bug so much to do because you're going to want to jump to the final part. But I urge you, don't skip things. The thing I'm going to try and teach you with free fall is the very beginning of our class is have a strategy. That strategy involves a couple of simple things that you should do every time so that you never make a mistake. You might think, oh, I don't need to do that. I can just figure it out. I'm good. The point is you're going to eventually reach a problem that you're not going to know how to solve. So you have to have a strategy or an algorithm. I call them algorithms. It's an algorithm. It's the closest thing I can teach you to how to solve these problems every time the same way, even though every problem is different. So with the constant acceleration, with these free fall, with the projectile motion, what I want you to do is start by drawing. In fact, everything we ever do. You know, there's the trope of a physicist with a whiteboard. I have a whiteboard. When I do a problem, no matter what problem, I have to write things down. I have to draw. So draw. In fact, we're going to learn how to do drawings that actually help us in chapters 5 and 6. But for now, just draw a picture and get it straight, because sometimes you can see in a drawing where your mistakes are. We know that we have a vehicle, so it doesn't have to be pretty. This is my little car. It starts here, and I'll call this X is 0, and it ends up somewhere. I'll call it X final. I don't know what it is. I know that it accelerates for 5 meters, or at 5 meters per second for 10 seconds. And I need to find X final. Second thing, your variables. Now note, we have X initial, X final, B initial, B final, A, and T. Those are the 6. Those are the only 6 we have. Sometimes we need to write them down for different positions, and we'll talk about that. But for now, for this problem, we need to write them. Now you read the problem and fill in these variables. We're told that the vehicle starts from rest. Rest means V initial is 0. We're assuming everything is in the X direction, positive X direction, by the way. We're told it accelerates at 5 meters per second squared for 10 seconds. All right. So now we're left with, well, what do we want to know? How far? How far is another way of saying we want to know X final. And we're left with 2 variables we don't know. Well, we actually can choose X initial to be 0. We need to start measuring from somewhere. Let's choose it to be 0. We can always make that choice. It's a measurement of a displacement. Displacement is delta X, which just means we just need to calculate the change. So we can choose that to be 0. What about V final? Well, we don't know it, but we also don't need it. We weren't asked for it. In fact, that's going to tell you how to choose the equation. You have 4 equations here. And I didn't want to draw my way through that. We have 4 equations here. And let's look a little bit deeper. What's not in this equation? There's no x in this equation, right? There's no, well, I'll come back to it, but there's no v final. So no x, no v final. Here, there's no time. Here, there's no acceleration. So those equations, these 4 equations are your only tools that you need. And you know specifically, because we don't have v final and we don't care about v final, we know which equation we're picking. We're picking the one that doesn't depend on v final, right? That's, if I write this equation down, x final minus x initial is equal to v naught t plus a t squared over 2. I know there's no v final here. I don't have it. I don't need it. Then I can just start putting in, this is 0. This is what I want. This is 0 because it started from rest. This is 5 meters per second. So this becomes x final is, well, I'll write it symbolically still. A t squared over 2, which is 5 meters per second squared times 10 squared over 2. 10 squared is 100. This is 500 divided by 2. So x final is 250 meters. All right. Simple enough, right? The algorithm is this. And I'll give you, well, you can come back and do it yourself. So this is our algorithm. Draw, write your variables, choose, equation, solve, right? And again, you only have v final is equal to v initial plus at. X final minus x initial is v naught times t plus at squared over 2. V final squared minus v initial squared is 2a times x final minus x initial. And x final minus x initial is v final plus v naught over 2 times t. Going back to this, could we have solved it a different way? Absolutely. In fact, let's do that. We knew that a was 5 meters per second squared, and v naught was 0, and t was 10 seconds. I could find v final from v initial plus at is equal to 0 plus 5 times 10, which is 50 meters per second. Now that I have v final, I could use any equation I want to find x final. And there's nothing wrong with doing that way. It takes a little longer. Sometimes when I do problems in class, I'm going to do them the long way. It's okay. There's different ways to solve these problems as long as you get there and you know the equations to use. When we do exams, the first thing on every problem that I have you list is concepts and equations relevant to that problem. The reason for that is I want you to build up a toolkit, a set of concepts and equations to use to attack various problems. In this problem, or these types of problems, the things to remember is that rest equals v naught is equal to 0 if it starts from rest or ends at rest. Constant v means that a is 0, and those equations. For now, that should be enough to get us there. I also will say this. When we go through tests, I usually take a problem like this and I break it up for you. So the first thing I'll ask you is, give me a couple of concepts and equations that apply to this problem. Then I have you give me the variables. Then I have you give me the equations and solve for whatever I want you to solve for. And then I usually have you change the problem in some way. We'll get to that when we get to exams. But essentially, this is exactly what I'm going to need to see on an exam. I'm going to need to see some kind of little drawing, some variables written, the equation written symbolically, and then solved, right? You usually have to do some algebra. Now, here's a bit harder problem using those same equations. We have a vehicle starting at rest, accelerating for 5 meters per second squared for 10 seconds. It then ceases accelerating and travels at constant velocity for 100 meters. We want to know what the constant velocity is, how far it went for the total trip, and how long in seconds did the total trip take. So, first of all, we need to draw this. We have two distinct regions. We have this, right, which is 10 seconds long and has an acceleration of 5 meters per second squared. And then a second part of the trip where v was constant. That implies that a was 0 and it went 100 meters. So in this section, I'm going to call this I and call this II, or 1 and 2. In this section, we know how far we went. We know we had no acceleration and v was constant. This section is exactly the same as last time. But as I said, we wanted to find v final, so we can do this with if it started at rest, that was 0. So we get that v final was a t, which was 5 times 10, which was 50 meters per second. We also need to know how far it went. There's a couple ways we can do that. We'll do that in a minute. Well, actually, I'll do it right here. We have x final minus x initial is equal to v naught t plus a t squared over 2, which we did do already, right? 250 meters. So x final for part 1 was 250 meters. So we know the whole trip was 350 meters. It was 250 meters here, and we were told already that it was 100 meters here. So we just add them together. How long did the whole trip take? Well, we know this part took 10 seconds, and we know this, we traveled at a constant speed of 50 meters per second, and we want to know the time, okay? So again, writing like this, I'm doing them backwards, sorry. X final, V initial, V final, A and T, 0. Remember, this is only for part 2 though, okay? So we could do a couple things with this X. We could do that, we could start from a new 0 here and go 100, or we could start at 250 and go to 350. I'm just going to go 0 to 100 because I only care about the second section time. So 0, x final is 100, v initial was 50, v final was 50, it's constant. But really, I don't need to do that. Let's look at these for a quick second. And I'm just going to look at the top 2. No, I'll look at all of them. Now, what happens when A is 0, when B is constant? What happens here? Well, if A is 0, we get that V final is equal to V initial. If A is 0, we get that V naught T is equal to X final minus X initial, or V naught is X final minus X initial over T, which is another way of saying change of X over change of T, as it should be. Here, we get that V final squared is equal to V initial squared, which means that V final is equal to, if I take the square root of both, plus or minus V initial. That's a little bit different than what this is saying. And here, this equation, if v final and v initial are the same, then we'll just call them v. We get 2v. So we get v t is x final minus x initial. So when you have constant v, a is equal to 0, and the only equation you really have is that v is equal to x final minus x initial over t. Going back to this, we know that v is equal to x final minus x initial over t. We want to find t, so t is equal to x final minus x initial over v. X final is 100 minus 0 divided by 50, so t is 2 seconds. So T1 was 10 seconds. And if I add T2, that was 2 seconds, we get 12 seconds. So the total trip took 12 seconds. And the total trip went 350 meters. The constant velocity was 50. You need to do them separately. There's a couple problems like this in the homework. One where you're going to a job interview, but you move at different velocities, and you just need to do this kind of thing where you solve each section for distance and time separately, and then add them all together at the end.
Professor, how did you get 2 seconds? Because I did 100 minus 0 divided by 2, and I get 50 seconds.
By 50.
Why is it divided by 50?
Because the velocity is 50 in this section.
Oh,
Where'd you get 2 from?
I was trying to, I was getting confused with all the equations you just wrote on the last on the slide before.
Let's go through it one more time. So in this first section, we know that we went, A was 5 meters per second squared, and the time was 10 seconds. X final, X initial, V final, A, and T. And we started from rest, so V initial was 0, and we're going to say that X initial is 0. And we need to find both X final and V final. So this is 0, this is 5 meters per second squared, and this was 10 seconds. To find X final without knowing V final, we use this. A t squared over 2, which is 5 times 10 squared over 2. That's 100, so that's 500 over 2 is 250. To find V final, we use V initial plus AT. Again, 0, 5 times 10 is 50 meters per second. For the second section, we know that we went 100 meters. We know that the velocity was constant, so A is 0. V was constant. And the V here is the same as the V final in section 1. So V is equal to V initial is equal to V final is equal to 50 meters per second. We know how far we went when we want to find the time. So V final is equal to V initial plus AT. That doesn't help us because this is 0. However, the one that doesn't have the one that doesn't have V final, but since they're the same, this is 0 because there's no acceleration. We know this is 50, so solving this for this is 100 divided by 50, and we get a time of 2 seconds. So we know the total time, we know the total distance, and we know V final. Does that make sense, Sammy?
Kind of, but at this point, I'm just going to give up and just try to figure it out on my own.
Okay.
Because I don't want to hold everyone back with my stupidity.
You got to draw a picture so that you know what you're talking about. You've got to write variables. You've got to understand that when constant velocity, you have 0 acceleration, that rest means the velocity is 0. And if we launch something up in the air and it comes back down at the top of its motion, which we'll get into in free fall, V is 0 instantaneously. So if you throw a football or baseball or a pen up in the air, it momentarily changes direction and comes back the other way. That momentary change, at that instant, the velocity is 0. That's really useful. You'll see in a minute, but we'll get there. So the algorithm for solving constant, choose your relevant equations. You only have 4. I cannot stress this enough because this is the step that everyone gets confused on. This equation, no x. This equation, no v final. This equation, no time. This equation, no acceleration. So since you have to write down, I hate when my PowerPoint does that. Since you have to write down the variables, and you've gone through and you've figured out which ones you know and which ones you want to solve for, if you know that you don't need acceleration and you don't have it, right? You immediately go to the equation that says no acceleration. That's why we have these 4. So in the last problem, we had no x and no v final. A was 0. We had A. I shouldn't say we don't have it. If you have constant, you know A is 0. What happens is you get, if v final is equal to v initial plus at, but you have constant velocity and A is equal to 0, these equations simplify a lot. Because if A is 0, they go away. That's not what I'm saying here. I'm saying this equation doesn't have A in it. So maybe you know there's an acceleration, but you don't know what it is, and you weren't asked to solve for it. So you have no idea what the acceleration is, and you aren't asked to solve for it. You immediately know that you're going to use that bottom equation because every other equation has acceleration in it, and you would have to find it. For instance, in that problem, we didn't know v final. Every equation has v final except this one. Stop. Except this one right here. So if you don't know v final and you don't want to solve for it right now or ever, you're going to go straight to that equation. You're taking a test and you're trying to solve for like x final and you don't know v final and you don't want to solve for it, you go right there. You could always solve for v final and use one of the other equations, but what I'm trying to get at is you're trying to take the test and you're stuck and you don't know what to do. You're completely lost. You write your variables, you figure out which ones you know and which ones you don't, and then how do you choose the relevant equation to use? You pick the one that doesn't need something you don't have, right? You'll see that in a minute when we get there. We'll do this over and over again. So I'm just trying to help you. You might think that, oh, I've got this. I can figure this stuff out. What I'm trying to tell you is take your brain out of it. Use your brain to figure out what the variables are. But at the point where you're looking for what equation to solve, to use, it's really easy. We have 4 of them. Okay, we technically have 2 more if A is 0 because A goes away, but for constant velocity. But once you've figured out what your variables are, which is thinking about the problem and drawing the problem to figure out the variables, choosing the equation should be a no-brainer. Your brain shouldn't even need to turn on, and then solving. That's what I'm trying to get at. So how do we make it harder? Well, there's a few things that you really need to know. In this problem is going to demonstrate something important, something really, really important for when we get to projectile motion. So in this problem, imagine that you're on a motorcycle and you're getting ready to shoot off the line, right? So you're getting ready to give it gas. And right as you give it gas, a car comes flying by that has constant V. So right as you take off, the car takes off. So yeah, Sammy, on that, when A is equal to 0, the x final minus x initial equal to vt plus at squared over 2. If A is 0, remember that v final is equal to v initial, so we'll just call it v whenever you have constant v. Might as well just call it v. Solving this for t, we divide through by v initial or v, and we get x final minus x initial is v. But you already should know that v is x final minus x initial over t. When the acceleration is 0 and we have constant velocity, you can just find what it is by finding the change of position, which is also called displacement, divided by the time. So in this problem, you're on a motorcycle that accelerates from rest at a rate of, no, it's fine, Sam. You're not the only one, I'm sure, that's confused. It's confusing. You have to do problems though to kind of get it down. Here we have a motorcycle that accelerates from rest at a rate of 22 meters per second squared. I'm going to do the variables again and all that stuff. At the moment, it takes off. It begins accelerating. A car that has constant velocity passes the motorcycle. And we want to know how long in seconds and where, how far away from where they started, does the motorcycle catch up to the car? What is the motorcycle's velocity at that time? This problem, oh, seems tough. This is the type of problem that you may have no idea how to start. How you start is exactly what I said before. Write down variables. So for the motorcycle and for the car, all we do is write down these variables, same variables, so that they each have their own set. Okay. Now, what do we know? They both start at 0. We're going to start measuring at 0. We know we want to find x final. I'll come back to that in a second. What is the initial velocity of the motorcycle? Well, it's at rest. Its acceleration is 22 meters per second squared. I don't know what v final is. In fact, I want to find v final. I don't know what the time is. So I have 3 things I don't know. I don't know x final for the car. I know that v initial was 30 meters per second and v final was 30 meters per second. So this is 0. It's traveling at constant velocity. Therefore, it has no acceleration. I don't know time. So I need to find out where they catch each other. And what does that tell you? Well, I don't know what x final is, but x final for the motorcycle has to equal x final for the car. Also, the time has to be the same. They both take the same amount of time to get to wherever they catch each other. Because what's going to happen is the car is, after some time, going to be here, and the motorcycle is going to accelerate and eventually catch up to the car, right? We want to know the time. What's that?
Well, how do you know that? Is it just you're supposed to intuitively know that they're gonna end in the same spot?
Yep, they have to. It's physics, right? If a car passes you and you can out accelerate that car and that car is doing constant velocity, you're eventually going to catch up to it. You hope. I mean, maybe you don't. Maybe it's going so fast that you could never catch it. But
wouldn't the velocities have to be the same for that to be the case?
nope, your motorcycle going to cover some distance, right? It starts at rest, but it's going to be covering distance. And at 22 meters per second, it's going to be going much faster than the car after 2-3 seconds. It's going to be flying, right?
Okay.
The other problem with these, to be honest with you, the problem with these dumb questions, and I call them dumb because they're made up by a physics teacher somewhere, is what if you can't get to a speed, fast enough to catch them?
Yeah, that was my next question.
The
Like,
motorcycle, obviously, if you guys don't know, about 2.1 miles per hour is equal to 1 meter per second. So that car is doing about 60 miles per hour. It's not like the motorcycle can do 400 miles per hour if it had to catch it. We're going to assume that it can just accelerate until it catches the car, But the real takeaway here is the algorithm of solving this and understanding that they're going to end up at the same X final. They're going to end up taking the same time to get there. The difference between them is how they do it. And so you'll see how we can use those two things to solve
Okay.
them. Yes,
Do they start together?
they start at the same point.
But not the same time, because it doesn't.
No, and the same time. They are at the same initial position when time is 0 and X is 0. And
Oh,
they
they
end up at the
stop
same.
together at the same time, at the same point.
Yes, one is got constant velocity, the car, and one has constant acceleration, but starts at rest.
Oh, okay, thank you.
That's why we write this stuff. Now, we want to solve either for time or X final, and then come back and get the V final. So check this out. For the car, because the car has no acceleration, we know that we have V of the car is X final minus X initial over time. We know that's it. That's the only real equation we have for the car. For the motorcycle, we have X final minus X initial is equal to V naught T plus A T squared over 2, but the motorcycle starts at rest, so that term doesn't exist. Or V final squared minus V initial squared of the car is, motorcycle, is 2 times the acceleration times X final minus X initial. I don't want to use that. In fact, I'm going to just use this one. So let me just erase that. From the motorcycle, I know this is true. And from the car, I know this is true. So I have X final, and because I'm going to say that that's 0, I have X final is equal to AT squared over 2. I also have that X final is equal to V of the car times T. So this is A of the motorcycle. I can put these together because X final is the same for both of them. And so I get A of the motorcycle divided by 2 times T squared is V of the car, the constant velocity times T. Solving this for T, so multiply by 2 over A divide by T, and I get these terms cancel, these terms cancel. So I get T is equal to VC times 2 over A. The car was doing 30. The motorcycle was doing 22. So this is 30 times 2 times 30 divided by 22 is 2.73. So T is 2.73 meters. Now that I know that, I can
Second,
put,
it should be second.
isn't,
I guess,
oh, okay, yeah.
I can do this for the car, but since they're the same, we can just plug it in. This was 30 times 2.73. So they met at the point 81.8 meters away from where they started. And a time of 2.73 seconds. The last thing that I can do is for the motorcycle, because V final is equal to V initial plus AT. And this was 0 because it started at rest. And this was 22 meters per second times 2.73. The motorcycle will be doing 16 meters per second when they pass each other, well, when it passes the car. So the point here was, you're staring at this problem and you don't know what to do. The first thing you do is you got to get straight in your head that they're going to start at the same point and reach the same final point they're going to do it in the same amount of time. Nowhere in this problem does it tell you that. You have to know that. You have to be able to understand that. Then you write down these 6 variables for each one of them. And you go through the question and you know what you're being told. If you're being told that something starts from rest or comes to rest, that means at that time its velocity is 0. We can always assume our initial x is 0. That's where things get a little messy, but in this case, we're going to assume that they're starting at 0 to make it easier on ourselves. We're told the acceleration of the motorcycle, and we're told that this is a constant velocity problem, right? Which means that the car is doing a constant 30 meters per second, but it also means the car has no acceleration. And then the last key point here is that the time and the position being the same lets you link the equations for the car and the equations of the motorcycle together as we did here. So you can link them together and then solve for an equation that you actually only have one variable that you don't know. Because otherwise, in this equation here for the motorcycle, x final is equal to at squared over 2. I don't know x final and I don't know t. In this equation for the car, I don't know x final and I don't know t. I have 2 unknowns, but I can substitute those 2 equations. A t squared over 2 is x final and x final is bt. I can substitute these 2 equations into each other. So I can substitute bt over there and then solve for t. I could do it the other way. I could substitute in for t that t is x over v, and I could put it in there. So I have x final is a x final squared over v squared over 2 and solve this for x final if I wanted to. But look what I get. I get 2 v squared. Oh, did I screw that up on the other side? No. Okay.
Professor.
Yes.
So the question says, where does the motorcycle catch the car? Which part of the equation did we solve for that? Was it when?
So what I did initially
Mhm,
was I solved for time.
right.
And when I got the time, I plugged it into here.
Right. And that time is where they'll both be, you answered the first part first then.
Yeah, but I
Like-
could have done it this way. I could have found x final and then plugged it in here to get the time. It's really up to you.
Mhm. But like this whole problem solving is based upon the fact that we know that they'll be in the same position at a certain point.
Yep. That allows you to set the equations equal to each other.
Yeah.
Yeah.
Okay. I see. So you just oh my sorry, my Siri got activated.
Oh, sorry.
You just yeah, I think I got it.
Okay.
You just offer the time first.
Yeah. So
But you could have done it the other way around.
right.
Okay, I see.
So here's this same problem done in a slightly different way. So now instead of them meeting, they're still going to meet, but now they're starting 100 meters apart.
Mm,
And this motorcycle is doing the same thing. It's taken off with some acceleration, and they're going to meet somewhere in between here. The only difference on solving this one, motorcycle, so we'll go through this all over again really fast, car, is that now we need to choose the correct X initials for these guys. So we need to be really careful about our signs and our initial conditions. So the car is traveling north, which means I should really redraw this correctly. So the car is traveling north. I'm not going to draw the car traveling north, but it's going north at 20 meters per second. Car B is traveling south at 25. So this is car A, this is car B. And if they're initially 100 meters apart, when do they meet? You might go, oh, I can do this. It's actually easier to just do it this way. I was thinking for some reason that I put the problem with the motorcycle that way, but I wasn't. All right, so car A is traveling north. We're going to assume that up is y positive. And we're going to use y's here. So let's change these to y's. That doesn't change anything in the equation other than rename all the x's y's. So initially, I'm going to say A is at 0. I don't know what y final is. V initial is 20 meters per second. And I don't, well, I know that because it's constant, A is 0, I don't know the time. But B is traveling south at 25. So I'm going to call down negative. So this is negative 25 meters per second. Again, I know it seems redundant, but if you do this, you'll always be okay. And we're starting with B at 100 meters. It's not at 0. A is initially at 0. So they're 100 meters apart. Stop it. Right? A and B. A is traveling north, B is traveling south. B is initially at 100 meters, A initially is at 0 meters. Now, you might be able to solve this in your head and figure it out, and that's fine. But if you can't, so we have the only equation is x, well, y. Y final minus y initial is V times T. Okay. And we have the same thing for A and the same thing for B. But what is the same? Y final is going to be the same for both of them. And T is going to be the same for both of them. So we can solve these two equations by substituting for T or substituting for Y final. Let's substitute for Y final. So Y final for A is Y initial of A plus V of A times T. Y final is Y initial of B plus V of B times T. But remember, we said that Y initial of A was 0, so we can get rid of that. So,
Professor,
yes.
I have a quick question. For the y sub f minus y sub 0a equals VAT, which of the original 4 equations is that derived from?
With A equals 0.
Thank you.
All right, so let's solve this for T. I get VAT minus VBT. All I did was I moved that over. I'm going to combine like terms. And so solving this for T, I get that T is Y initial of B over VA plus VB, which is 100 divided by, what were they?
Should be negative. It should be minus, not positive.
Yeah, you're right, sorry. I'm jumping ahead of myself. VA was 20 and VB was negative 25. So they add together, right? So that becomes 100 divided by 45. So T is equal to 100 divided by 45, which is what? 2.22 seconds. And then we can use either of these to find Y final. So we can plug in for Y final here. Y final is equal to y initial of a plus v of a times t. That is again 0. This was, what did we say, 20 times 2.22, which is 44.4 meters. I left off the 0.4. Let's make sure that we get that for b as well. Y initial of b plus vbt. So this was 100 plus negative 25 times 2.22. 100 minus 25 times 22.2 is, oh, sorry, I'm dumb. 100 minus 25 times 2.22 is 44.5. So this was 44.4-ish. This is giving me 44.5. There's a little discrepancy from rounding. But either way, they would give us. The big reason why I put this on this PowerPoint, though, is make sure that you're always listing your variables. Make sure that your signs are correct. These are vectors. So V has a sign. In this case, A and B, their velocities were in opposite directions. A was positive, B was negative. And then you only can solve this if you assume that they're going to meet at the same time. So their equations are linked by time, right? So what we did was we used this equation, x final minus x initial is equal to Vt for both of them, and we linked them using t, or x final. Or as physicists say, you always have to have the same number of equations as you have unknowns. We didn't know the final coordinate of y, and we didn't know time. So we had to have two equations so that we could substitute one into the other. All right, that's all fun and blah, 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 blah. We could do this again. I'm pretty bored of doing this, and I want to do free fall anyway. This is the same thing. You'll see we'll do free fall. If we have time, we'll come back to it, but I don't think we will. All right. So free fall is exactly the same thing, except for two small things. When you launch something straight up and it comes back down, at the top of the motion, the velocity is momentarily 0 or instantaneously 0. So at max height, we say that the velocity is at max h, v is 0. And then when it goes up and down and comes back down. And then the other thing is that all of our equations, we're going to change x to y, but we're going to substitute, instead of a, we're going to put minus g. So here where we had x final minus x initial is v naught t plus a t squared over 2, we're going to plug, instead of plus a, minus g t squared over 2. That is because a is equal to minus 9.81 meters per second squared, which is minus g. G is equal to 9.81. I cannot say this again loudly enough, firmly enough. Someone always messes this up. G is the acceleration due to gravity at the surface of the Earth. It has a value of 9.81 meters per second squared. It does not have a value of negative 9.81. Wiley uses 9.8. We'll talk about that later. Which means what you cannot do is, this is not minus 9.81. Don't make that mistake. The reason it has a negative sign is because we are assuming always in free fall that the center of the Earth is down and y is positive away from the center of the Earth. So as you go up away from Earth, y has to be positive in order for the acceleration to be in the negative y direction. So this is negative ay, which is equal to negative g, which is equal to negative 9.81 meters per second squared. The other equations are V final is equal to V initial minus GT instead of plus AT. V final squared minus V initial squared is minus 2G Y final minus Y initial. We'll come back to that. So Newton's question of dropping an apple from the ground. Draw a picture. Make sure that you label Y. This is Y positive going up. The object's going to fall. A is equal to minus G, meaning it's down, opposite. We do the same exact algorithm that we did for constant acceleration. That's why I want to teach you it that way. It might seem tedious to write AY in free fall, and I admit it is a little bit, but it makes it so that you don't make mistakes. We're dropping a ball from a height of 43 meters. So this is Y initial, which is 43 meters. Y final is 0. So it starts at 43, ends up at 0. V initial from rest, 0. I don't know V final. I don't know the time. So as before, we have those same 4 equations, except now you need to make A minus G. And I'm just going to write these 3 for now. They'll get us through what we need for right now. These are the same exact equations we had before, and you use them the same exact way, except A is now minus G. So if I want to know the final velocity and I don't know the time, this equation has no time. I know that I started from rest, so I can get rid of V initial is 0. So I get V final squared minus V initial squared is minus 2G Y final minus Y initial. Plugging in variables, this is 0. Y final is 0. The negative signs will cancel. I get V final squared is 2G Y initial, taking the square root of both sides. V final is plus or minus 2G Y naught, which is equal to plus or minus 2 times 9.81 times 43. Now, should V final be positive or negative? Plus or minus 29?
Negative.
Yeah, negative. A lot of times in these, you need to make sure that when you're taking a square root, which happens because we have time squared and we have velocity squared, that you need to make sure you know which direction you're talking about. So our V final is negative 29 meters per second. It is, when it hits the ground, it's going in the negative direction. Once I have that, if I want to solve for t, I can use V final is V initial minus GT, get rid of that. Remember that this means t is V final divided by negative g, which is negative 29 divided by negative 9.81, not negative 9.81. This becomes 29 divided by 9.81, 2.95, or yeah, 2.96 seconds. One thing you might have noticed, I hope you noticed, with all the constant acceleration equations, once you find one variable, the first variable, all the other variables are super simple to solve. Usually the first one, you have to like substitute in one equation into the other, especially when you're talking about like 2 objects. But once you have that, the rest of it falls apart like a puzzle. It just, everything just pops into place. The idea is that I want you to write your variables and get used to writing your variables, drawing some kind of picture to help you figure out what those variables are. And then choose your equations based on what variables you don't have. Here, we're going to do the same as before, but now someone threw it down. So it's going to have everything the same, but now its initial velocity is negative 8 meters per second. It's still going to go from Y initial is 43 to Y final is 0. Remember that as you go up, in Y, it's positive. So this isn't 0 and this is 43. This is 0 and negative 43 because this direction down is negative. Our acceleration is negative g. So writing these, and I'm not going to solve the whole thing, but y initial 43 meters, y final is 0, v initial is now negative 8 meters per second. I didn't know what v final was. This is negative 9.81 meters per second squared. I don't know what the time is. So again, not having time, let's use v final squared minus v initial squared is equal to minus 2g y final minus y initial. Again, this is 0, but this is not going away now. So this is v final squared. Move it over, add v naught squared to both sides. Minus 2g, but it's minus 2g times minus y naught. And then taking the square root. So now this is v final is plus or minus v initial squared, which was negative 8 squared, plus 2 times 9.81 times 43. And that is 64 plus 2 times 9.81 times 43. Square root of that answer is 30. So it's going to be negative 30.13. Now it might surprise you that when we dropped it, we got negative 29. When it was thrown down, it ended up doing negative 30. It would seem like you could just add 8 to the negative 29, right? Nope. It ends up not having a huge effect on the final velocity. I mean, it does have some effect, but it's not a huge effect. That might surprise you a little bit. That's one of the things about physics. Your intuition almost always proves you wrong. If you meet a lot of physicists, especially when we get to our 3rd year of undergrad, most of us are shell-shocked with how dumb we are because our intuition's always wrong. My intuition would say, yeah, it's going to go a lot faster if I throw it down than if I drop it. Nope, not true. It's a little weird. So what about going up now? Can I go back a slide to which slide? This one, Lewis? Or this one?
Slide 33. Yeah, that one.
Okay.
Thanks.
Whoa. And I'm recording this, by the way, so you can always come back to it too. But let me know when we can move on, because I have one more that I want to go through, and then we'll talk about homework, and then we'll be done.
I'm good. Thank you.
Okay.
Professor,
Yes.
sorry, I think I'm making a simple algebraic error, but how does a 2g become positive?
Where? In what?
Right before you square root them on the yeah.
Because I'm multiplying negative 2g by y final minus y initial, but my y final is
Oh, I
0.
see. Okay.
So the
Got it.
negatives cancel.
Right. Okay. Thank you.
Yeah, no problem. All right. So if we kick a soccer ball, if you've ever done this, it's a little weird, but go to kick a soccer ball and it shoots straight up in the air. Okay. So we kick it with an initial velocity of 12 meters per second. It should say in the positive y direction, but we're in one-dimensional motion, so we're assuming it goes straight up. How high does it go, and what is the velocity when it hits the ground? So you're kicking a soccer ball at about 25 miles per hour, which isn't bad. I mean, yeah. So I made up that number. I don't know how hard a soccer
12 meters per second. That's a lot.
is it. All right. Well, a baseball is thrown at about 45 meters per second. So
Oh,
I don't know. I don't know if that's a lot or not. I'm thinking it probably not. I mean, a good striker can probably get it going. Anyway, besides the point, doesn't matter. So now we're going straight up and it's going to come back down. And we need to talk about this a little bit because there's a few things we can do. Let's just talk about going up to maximum height. Yeah, so 34 is about 17. Using 2.1, maybe 16. So yeah, it's probably a good speed for a good kick. Thanks, Eric. So we know that y initial will be 0. We have to go up. Y final, I'm going to call h. I don't know what it is. I don't know what h is. Gravity is still negative 9.81, still downward. And there's a few things that I know. I know my initial velocity is positive 12 meters per second. And I know when it gets up to h, wow, yeah, 36 meters per second is crazy. I know when it gets to maximum height, the velocity final there is 0. So when it reaches its maximum height, its velocity is 0. It still has the same acceleration. So we're going to find out how long it takes to get up there and how long it takes to come back. We do the same thing, y initial, y final. I'm telling you, you're going to get so annoyed with writing these, but it's the best way to make sure you don't make a mistake. So our y initial is 0, our y final is h, but we don't know it, we want it. We're going to find that right now. Our v initial was 12, positive. Our v final is 0 at max height. Our acceleration is negative 9.81, and our time is unknown. We're going to come back to the time too. So let's find out how high it reaches max height. Remember that we had those 4 equations and we didn't know time. So we had one that didn't have time. And that is this one. Okay. This one has no time. We know v final, we know v initial, we know g, we know y final, or I mean, we want y final. Yeah, Alejandro, at the top, it momentarily has an instantaneous velocity of 0 as it changes direction and starts falling back to Earth. The acceleration is always the same. It's always gravity. But the velocity is momentarily 0. It still has acceleration there. The Earth is still pulling it back. It's just stopped its upward motion and it's starting to have downward motion. So our y initial was 0. So what we get is we get v final is 0. So we get negative v initial squared is equal to negative 2g. I'm going to call y final h. Negative signs cancel. I want to solve this for h. So I get v initial squared over 2g. And my v initial squared I said was 12 squared over 2 times 9.81. So the maximum height that would go is 12 times 12 divided by 2 times 9.81. 7.34 meters, which is about 20 meters, about 3 feet. So it went about 22 feet up, which is pretty high, I guess. Not great, not really that high. And then if we want to know the time, now that we know the maximum height, we can use y final minus y initial is v naught t minus gt squared over 2. And check this out. This kind of sucks. Or we could use v final is v initial minus gt. This to go up, we know that v final is 0, so we can solve this for t. But think about this. Y final minus y initial is v naught t minus gt squared over 2. And we want to solve this for time. We know y initial was 0. Let's set this equal to 0 and move some stuff around. Moving this over and solving for 0. Now we get a t squared plus bt plus c, where a is minus g over 2 or minus 9.81 over 2. B is v naught, which we said was 12, and c is negative y final, which is negative h, which we said was what, 27.34 meters negative. So this is c is negative 7.34 meters. And then you have a quadratic, which is negative b plus or minus square root of b squared minus 4ac over 2a, plugging those values in to get time. That's not bad if you're good at quadratics. You can do it. In fact, sometimes you have to do it. Or you could do this, which is much easier. We already found the time to go up and the time to drop. So the time to go up, we found. But let's think about the whole problem as like this and rewrite our equations and see what this tells us. Now, when it goes up and comes back to the ground, these are both 0. Where it left from and where it comes back to are 0. Its initial velocity was 12. A was minus 9.81 meters per second squared. And we don't know t for the whole time. So this is the whole time. We only found t up. So let's find t up here. So t up, y initial, y final, v naught, v final, a, and t. We're just going to call this h, and I'll write that it was 7.34, whatever it was. I don't care what it was. 0, v initial was 12 meters per second. At the top, it was 0. Remember that I'm only going up to max height, minus 9.81 meters per second squared. So the time to get up there, if we do, which one do I want to use here? Well, let me actually flip this around. I'm going to actually do something a little bit different. The time to fall. So the time to fall, y initial will be 7.34 meters. Y final will be 0 because it reaches the ground. V initial will be 0 because at the top of its motion it had 0. V final, I don't know. So 7.34, this is 0. V initial will be 0. V final, I don't know yet. But symbolically, and this is what's kind of cool, to fall from max height, we know that V initial is 0, and Y initial is h, and Y final is 0. So the time to fall from max height is Y final minus Y initial is equal to V naught t minus gt squared over 2. But this term goes away, and this term goes away. Negative signs go away. So I get t squared is 2 y naught over g, or t is 2 y naught over g. The time to go from the top, from the ground back to the ground means that y initial is equal to y final is equal to 0. And we have y final minus y initial is v naught t minus gt squared over 2. These are both 0. So we get v naught t is equal to gt squared over 2, just moving that term over. And t squared is equal to, if I divide by t, actually, and I'm going to flip sides, t is equal to 2g 2v naught over g, right? So if I do t squared is equal to, do I want to do, nah, I don't want to do that yet. What I'm trying to get at here, so t is, and I forgot how to get there, 2v naught over g. I actually want it in the other form. Oh, let me use the other equation. So the last equation that we haven't used a lot yet was v final plus v initial over 2 times t. And when y final minus y initial is equal to v naught t minus gt squared over 2, when this is 0, you can solve this for v naught squared. So v naught t is equal to gt squared over 2, which is v naught is equal to gt over 2. And because v final is equal to v naught minus gt, v final is equal to gt to the half minus gt to the half, which means, sorry, minus gt, which means that v final is equal to negative gt to the half. Check that out. When we start and land at the same height, v initial is equal to negative v final. Okay? That means the speed that it goes up with is the speed that it comes down with. No, Sammy, we're not ignoring the other equations. We're just not using them because they don't help us. They're still there. We'd still have them if we need them. The point here is that the speed that it goes up with, if y initial is equal to y final, then v naught is equal to negative v final. They're the same value. Whatever goes up comes down, same speed. That's a weird fact. The time to go up is actually, now the time to launch up and the time to go down are actually equal. So let's call this t up and t down. The total time is equal to t up plus t down, and the total time is equal to from y initial from y final minus y initial is equal to v naught t minus gt squared over 2. When these are equal, you get 0 v naught t minus gt squared over 2, which becomes t is equal to 2 v naught over g, which means the time up is v naught over g, and the time down is v naught over g. And the total time is 2 v naught over g. That's cool. That only works if you start and land at the same spot. So when you don't, what happens is come on. When you don't start and stop, so let's say you throw it up and it goes off a cliff, and we're assuming that it doesn't really significantly move in the x direction. That means that you get a y initial, y final, v naught, v final, a t, but this equation now does not equal 0. So now this equation becomes a quadratic, and you have to solve it with minus b plus or minus b squared minus 4ac square root over 2a, where the term on the t squared is your a, the term on the t is your b, and the term on the c, but you have to move those over. The constant term is your c. Or you could find the time to max height and the time to fall, but t up does not equal t down if they have different heights. So try that out for yourself. The one nice thing about free fall is there's really only like dropping from rest, being shot up, being thrown down, you know, different heights, same height. There's only a few examples. One of them that I'm going to talk about in a second has a little wrinkle to it. So this last page here gives you the general, these are the general equations when a is constant. These are the ones you need to put on a post-it note and stick to your computer or write in your journal or whatever, wherever you keep your equations that you need to remember. If a is 0, you get these. Remember that rest means b is equal to 0. Constant v means that a is equal to 0. When a is equal to 0, you get these equations. X can be x, y, or z. We're talking about one dimension, but it can be any dimension. And then if you're talking about free fall, A is equal to minus G, and you just plug in everywhere that you get an A here, minus G, minus G, minus G, and you get these equations. And Y has to be positive away from the surface of the Earth. As you go up, you get more and more positive. But that's it for free fall. So I'm going to go to our Canvas page, and here's our homework 3 that's due a week from Thursday. The problems that I've selected for you to do. So here's a problem where you have to drive. So you drive for the first 100 kilometers at 100 kilometers per hour, and then construction work makes you slow down for a certain distance, and then you have to complete the third part of the trip. So here, all you're using is that x final minus x initial is equal to vt, but you have 3 different areas, and you need to find the time and the distance for each one when you're given only certain information. It's not hard, and I'm making a wreck of it trying to describe it, but basically you just solve the equation for each of those scenarios and then add them all together to find how much time you need at the end. Here's an electric vehicle starts from rest, so its initial v is 0, and accelerates for 2.1 at a rate of 2.1 meters per second squared until it reaches a final velocity of 20 meters per second. Then it slows at a constant negative acceleration of 1.2 meters per second squared until it stops. So you have 2 distinct times here. It starts from rest until it reaches 20 meters per second, accelerating at a rate of 2.1 meters per second. That's positive. Then when it's at that 20 meters per second, it decelerates until it reaches 0 meters per second, until it stops at a constant negative 1.2 meters per second squared. So you need to find how much time it takes to accelerate up to 20 at 2.1, and then back down to 0 at negative 1.2, and how far it goes. So treat them as 2 separate cases and just add them together. It's not too hard. Here's a hoodlum throwing a rock down. We did that one with the negative 8 meters per second. Just remember that when he throws it down, it has an initial velocity of negative 16. Question 4 is a hot air balloon. There's everyone here, pay attention. You're throwing a sandbag or a package or whatever over the side, but it's ascending at 12 meters per second. The initial velocity of the package is not 0. It's the same as the hot air balloon. So as the hot air balloon goes up, everything attached to it is moving at that velocity. It's just like throwing something out of your car. It's going to go the same speed that your car is going as it leaves the car. Air resistance will slow it down, but if you let something go, it still continues at the speed that everything was going at. So the bag is still going to be going up with a velocity of 12 meters per second, not 0 when you drop it. It's not being dropped from rest. It's being dropped with an initial positive velocity. Okay, so this is the same as the car and motorcycle. So I want you to do this one. It's the same thing as a car and motorcycle. Just remember that they have the same final position and they have the same time. Solve them separately. One has acceleration and no initial velocity. One has constant velocity and no acceleration. Okay. And question 6 is a sprinter. This is just like the one where you had to do one section, he has constant speed, one section he has acceleration, you've got to find the time. And then the last question is how far does the runner travel in 16 seconds. The area under the curve for a v versus t graph is the integral of v dt. So all you have to do is find the areas underneath these. And remember that this one's 4. It tells you that Vs, this top line, is 11 meters per second. So this first column is 4. I'm sorry, is 11 high, and it looks like 2 seconds wide. So this whole section is 22 of these, the area of these 4 squares, but you're going to take half of it. So it's 11. This area is 11 times 2, 4, 6, 8, so 88. This area is these 4 squares. This area, you have 2 squares and you have half of 2 squares. So just find the area under the curve and add them all together, and you should be fine. And that's it. This stuff, I really, you don't have to turn it into me, but I really suggest when you're doing these problems, particularly the hot air balloon and the hoodlum throwing, that you do practice it by drawing a picture and writing Y initial, Y final, V initial, V final, A and T, and just getting used to doing that. You'll be asked to do it on an exam. You'll be asked to do it on a quiz. And our quiz next week will be a free fall problem. So it'll be something where I want you to write the initial velocity or the initial variables and then compute like the time and the distance. So it'll be very similar to either this or the balloon problem. Okay. We have about 20 minutes of class time left, but we haven't taken a break. And I haven't taken a break. So if you guys have any questions that I haven't answered already on the homework, let me know. Otherwise, I'm done. Make sure that you got your quiz in. Hopefully you didn't find it too hard. Hopefully you had plenty of time to do it and found that it was really fast and easy to do. But if you have questions on homework that's due Thursday, not tonight, like I mistakenly said, feel free to ask. Otherwise, I'm done and I'm going to stop recording.
Can I ask a